So this evening, this is the second of a series of 4 lectures to talk to you about California's water, past, present, and future. And tonight we have 2 speakers. We have Jeanine Jones, whom you all met at the first class, and we also have Connie Woodhouse, who I will introduce in just a minute. And Connie's going to go first, and Jeanine will give the second lecture. But also, after I introduce Connie, Jeanine is going to give a little bit of context in terms of what the 2 lectures tonight are intended to do. Jeanine is the primary architect of this course and of that exhibit that I hope you've all seen by now on the second floor of the Aquarium. The little book that you have was made to go along with that exhibit, and so was the poster. Jeanine is a veteran of the California Department of Water Resources. She's how many years there?
30 plus.
30 plus. Yeah, 30 plus. And she's made huge contributions, I think, to codifying advances in the understanding of California's water system, the variability, the prospects for the future, and hasn't just summarized and codified those advances in understanding, but she has translated them into policies that make sense for this state from which we all benefit. On Tuesday of this week, I was up at the RAND Corporation for a policy seminar called California's Water Challenges. And the best thing about that seminar was the free bag that I got. I can say unequivocally that those of you who were here for the first class, you got a better overview of what's happening to our water system than you would have had you gone to RAND. So, now let me introduce Connie Woodhouse. Connie is an associate professor in the School of Geography and Development at the University of Arizona. She has joint appointments in the Laboratory of Tree Ring Research and the Department of Geosciences. Previously, she was a physical scientist at NOAA's National Climatic Data Center in the Paleoclimatology branch. Her primary research focuses on climatic and hydrologic changes and conditions in the past 2,000 years in Western North America, using tree rings to develop reconstructions of past rainfall, stream flow, and drought. She's also interested in the applications of scientific information and data to water resource management. She's served on national and international boards and panels, including the U.S. Committee of the International Quaternary Association, the American Quaternary Association, and the Tree Ring Society. She's been a member of several National Academy of Sciences studies of the management of the Colorado River and the future of hydrologic sciences. She received her BA in Environmental Education from Prescott College and MS in Geography at the University of Utah, and a PhD in Geosciences from the University of Arizona. So Jeanine's going to come up now and give some context for tonight. I want to encourage you to take advantage of these remarkable people and ask questions and have some dialogue. And so Bill, we've got handouts, you can get them later or you can get them now, because we want to really try to give a really good overview of these issues during these 4 sessions. And we will package something at the end of the course that you can use for whatever, whether you're a teacher or whatever. We're going to be a week behind in giving you hard copies of PowerPoint slides, but we'll catch up with everything at the end. So please welcome Jeanine for a repeat appearance.
Well, thank you, Jerry. Really, the thought process behind today's presentation stems from the overall theme of our exhibit, which is that change happens and that climate is highly variable. So we started out the first lecture last week with just an overview of California water to provide background. And then in this lecture and the next one, we're going to look at the extremes, drought and flood. Because in reality, when we manage water, we manage for extremes. We don't manage for average conditions, we manage for the droughts and we manage for the floods. So for tonight, Connie will be talking about some things that we've seen in the measured paleo record before our period of the historical record begins. And then when she finishes explaining how bad droughts have been in the past, droughts that are much worse than we've experienced in our historical period and much worse than what our water infrastructure is designed for, then I'll talk about some of the droughts that we have experienced, what the impacts of those are, and where we typically see impacts in drought, and just a little bit of a teaser for the fourth lecture of what the future might hold.
And let me just add a footnote. At this RAND seminar that I mentioned I went to on Tuesday, the speaker mentioned that they had gone back over 100 years and they felt that they had captured the extremes of droughts and floods that the state would have to deal with going forward.
He's not a water manager, obviously.
All right, so Connie?
Connie?
Now I think you're going to wear that lavalier and we'll turn this right off. So how many water people do we have in? We have Bill Cooper, the director of the Urban Water Institute at UC Irvine. So we've got a lot of expertise in this room.
All right, can you all hear me okay? Small enough room, I probably don't even really need the mic, but I'm happy to be here. I'm happy to talk to you guys. It's nice to see we have a pretty small group, and so if you have questions while I'm going through this, let's go ahead and address those instead of waiting to the end. I want this to be informal and interactive, so please feel free to speak up. So I'm going to be talking about California's droughts over time. My context for time is the last 6,000 years, which is a little arbitrary, but it's a time period which we have a fair amount of information about droughts in this area, and so I thought that was a good place to start. So I'm first going to talk a little bit about the modern record of drought for California and question whether it's representative of the long term, as the RAND representative or speaker suggested. Then I'll talk about the different sources of information that we have from the paleoclimatic records. And paleoclimate means climate before the time of instrumental records, so before the time of thermometers and rain gauges, at least in this country that they were making those measurements. Then I'll talk about some of the droughts that are recorded in these records, and then finally just talk a little bit about how we've got this great record of droughts in the past, and are they really relevant as we go into the future, which of course is the future of anthropogenic climate change. So to start with, is California experiencing a drought right now? This is the image of the drought conditions for the U.S. as of Tuesday this week. This is from the National Drought Monitor. And just the southern part of California shows a little bit of what's called abnormally dry. That's not even a drought category. So California's really not experiencing drought by this measure right now. But there have been significant droughts. I'm sure you all are aware of this. 2009, this is the map of drought. The focus being in Northern California, 2007, again statewide, but being concentrated in the southern part. So, of course, the state has experienced drought recently, even if it's not undergoing drought right now. And this is the statewide record of annual precipitation, so a different way to look at drought. So we're looking at 1895 to 2010. Each bar is precipitation. This dotted line is the average over time, and that orange line, which probably is hard to see, is sort of a smooth line, so you can see periods of drought a little bit better. And here's the most recent drought, 2000 to 2009, fairly severe. But if we go back in time, this drought was one that I think caused water managers some angst, 1987 to 1991 or so. But really the big drought that sticks out here is this one. From the 19-teens to about the mid-1930s, which is fairly persistent. Except for a little break here, it was a fairly long drought. So that's the statewide picture. We can look at some regional records of drought. These are precipitation records from Pasadena and Redlands from 1900 to about 2007 or so. These are the periods of drought. Some of these are the same ones we see in the statewide record, but we have some droughts going on in the southern part of the state that you may not see in the northern part of the state. So they show periods of drought. The question is, are these records really representative of the long term? At best, we have 125 years of record. A lot of the records that we have in the state and in the western United States are a lot shorter than that. So are these droughts that we see in the 20th and 21st century, are they representative of a longer period over the past? And are they a good guide for what we can expect in the future under natural variability? And we're interested in that, of course, because droughts have tremendous impacts. Here's some photographs. This is the American River in 1977, a really severe drought year. This is Tahoe Dam and Truckee River in 1988. Again, low flows, low reservoir conditions, and this is Lake Shasta in 2009. So these droughts have tremendous impacts on water resources, on fisheries, on riparian populations, on recreation, on agriculture, on so many things that we really need to know about these droughts and understand the character of them and the range of natural variability. And it's hard to do that with a record of just 100 years in spite of So where do we get information that allows us to extend these records back in time? Well, there's a number of different kinds of biological and geological recorders of climate that go back in time. I'm going to mention some of these. This is certainly not a complete list, but these are the ones that are more important for the Western United States and more important for recording drought conditions. Lake sediments and ocean sediments. We take cores from the bottom of these lakes and oceans and look at the sediment layers, and the sediment layers give us information about materials that have blown in to the lake or the ocean, like pollen grains, or materials or organisms that grew in the lake. So these kinds of shells and little tiny organisms that grew in the ocean and give us information about the temperature of the water based on the chemistry of their shell or the abundance of different types of organisms. So taking cores from the bottom of these oceans or lakes give us pretty long records. The lake sediment records go back probably thousands to tens of thousands of years. Ocean sediments can go back hundreds of thousands of years, so pretty long records. We can get records from sand dunes. If you, again, take a core from a sand dune, you'll find that the sand is interspersed with layers of soil, which are documenting periods of time when the climate was conducive to plants growing in soil development. And so those can also record periods of drought and periods of weather conditions. And those go back about 10,000 years. So these records are all quite long, but the information that we're getting is maybe one data point every couple of decades in the best case, or maybe a data point, a piece of information maybe every 100 years or more. So the time resolution is fairly coarse. If we want information on the order of a year, we go to tree rings. And tree rings, annual rings, we get information every year from a tree ring. The downside is that these records are much shorter. Trees, I don't know, how old do you think trees grow to be around here? What's the oldest tree do you think? A guess. Well, in California. Sequoias. But how old are they? How old are sequoias? A couple thousand?
Yeah, the bristlecone.
And the bristlecone. And how old are they?
5.
Close to 5,000, yeah. Those are unusual. Those are unusual trees. Your garden variety, Jeffrey pine or ponderosa pine is maybe not too hard to find something that's 300 years old or maybe 400 or 500 years old if you really look. So that's more the realistic range for the trees. We can extend them back in time with pieces of dead trees that I'll talk about in a minute. But annual information. We also get some information from archaeological artifacts and from more recent human artifacts, things like early written records from early measurements, or sometimes diaries which talk about weather events, or newspaper articles on weather. And we can get very fine information on the timescales of daily timescales. But these records are pretty short. I mean, how long have people been in California to write this kind of thing? Maybe since 1850. Maybe some of the missions, there may be mission records that are older than that, but these are fairly limited in length as well. Yeah.
How would indigenous populations, like I know it's not written, but they do pass stories of, old droughts or rains. How would that be taken into consideration scientifically since it's not actually written down?
That's a good question. I don't know about California, but I've started working with some of the tribes in Arizona, and I have a student that's doing a reconstruction of precipitation for the Hopi Reservation. And we're working with some anthropologists who are suggesting that we can take this record of droughts in the tree ring record and ask people what they remember about these periods. And there already is anecdotal evidence about droughts going back in time, and it helps us confirm what we're seeing in the tree ring record, and it helps them look at this record and realize that there's something else that's confirming what they're remembering as well. So it's kind of a validation thing, but it's also a tool, I think, for the for the tribal people to sort of, put what their knowledge in a context as well. Yeah.
In your sand dunes, how do you actually date that? I hadn't realized that you would do that too.
Well, there's two ways. Traditionally, the organic layer was dated with carbon-14.
Okay.
But there's also another method that actually dates the grains of sand. It's optical luminescence dating. So it's actually recording the exposure of the sand grains to sunlight. All right, so those are some of the basic ways. Let's talk about some of these records. We'll start with some of the longer records of aridity and drought in the last 6,000 years from lake and ocean sediments and fossil stumps. This is not from California. These are my graduate students taking a lake sediment out of a lake out of a lake in Colorado this summer, but it was the best photograph I have. Pretty small operation for little alpine lakes compared to what you use for ocean sediments, which is a full-on expedition to get those ocean sediments out. So I'll start with a drought that's documented through stumps that are rooted in the south end of Lake Tahoe. They're rooted in the water now. They grew, of course, when the lake level was lower. This is work that was done in 1990, and these stumps were dated with radiocarbon dating, so they didn't use tree ring, didn't actually do the tree ring dating, but they radiocarbon dated these, and it looked like these trees were growing about 5,000 to 6,000 years ago, and they're documenting a period of time when the lake was 12 feet lower than it is now. There's other evidence. This is a historic photo from the 1930s, so that was a period of drought in California. The lake had dropped a bit, and this is a bedrock mortar. These are little dips where they were grinding grains, and that documents that certainly the lake had to have been quite a bit lower for people to be doing that kind of work. So these two bits of evidence suggest that we had a period of aridity or drought. However, there were some questions. Was this due to drought, or maybe this spillway was lower and somehow the lake dropped? Was there another reason that the lake level was lower that wasn't due to drought? But subsequent work from lake sediments has confirmed that this was a period of dry conditions. The trees are, I think we counted about 350 or 400 rings on the trees. This kind of activity would have had to have that lake down for quite a while for that activity. So this is a pretty persistent lower lake levels and a period of aridity in this area. Okay, I told you we could use ocean sediment records. So here's a record from Santa Barbara Basin. This is going back 5,000 years. And it's the oxygen 18 isotope from one of the organisms that likes to grow in the top layers of the ocean water, and it is an indicator of sea surface temperature. So this is a record of the sea surface temperature. The blue is cold sea surface temperatures. Two periods of time are roughly around 1,000 years ago, roughly about 3,000 years ago. Well, we know now that when the temperatures are colder than average off the Santa Barbara coast there, that tends to indicate drought conditions. Like when we have a La Nina event, the temperatures are colder and drought is pretty prevalent over at least Southern California. So we think that these indicate periods of dry conditions. And we have support from the long bristlecone pine records, which someone suggested I think the oldest bristlecone is about 4,800 years old. And then it's augmented with some remnant material, which I'll talk about how that's done in a second. So this is bristlecone pine from the White Mountains and from the Great Basin. And this is low growth, the yellow, high growth, the green. These trees are limited in growth by moisture. So low growth would be dry periods. And these two dry periods coincide with those periods of cold sea surface temperatures. So that seems like it's a drought that's reflected in the sea surface temperatures, extending across California into the Great Basin. So we can look at this period of time here and look at some other evidence that further suggests this is a period of drought. This was also a period of time in which anthropologists found that there was a cultural shift in the people that were living along the coast of California from the dependence on terrestrial resources to marine resources. And that kind of makes sense. With the cold sea surface temperatures, those waters are more productive. So there's more fish available. During a drought, your terrestrial resources, plants and animals might have become more scarce. So this time period from 8450 to 1300 roughly coincides with this period as well. So another indicator that this was a period of drought. So when we do the paleoclimatic data, it's nice not to have to rely on one record, but to find several different kinds of records that can be used together to document these periods. Okay, let's look at some lake sediment records from Pyramid Lake. This is Pyramid Lake up here. I'm also going to mention some more stump records from Lake Tahoe, from the Walker River, and from Mono Lake in that area. So the lake records, again, can either be interpreted in terms of the materials that are blowing into the lake, washing into the lake, or what's going on in the lake itself, the water chemistry or the organisms that are in the lake. And so this particular record is looking at the oxygen isotopes, which are a reflection of the rate of evaporation, how much evaporation is happening in that lake in terms of hydrologic balance. And so when you have these positive values, that indicates drought conditions. So this is a record that goes back 3,000 years. These are all the droughts. You can see it's fairly regular, fairly periodic episodes of drought. There's a bit of a trend here from more severe to less severe, but in this case, this record is not very reliable for the magnitude. It's more reliable for the frequency and the duration of drought events. So this period, again, is around that period 1,000 years ago. 3 droughts occurring in that period of time. It's a period of time that we call the medieval period, and it was first recognized as a warmer period in Europe, in the North Atlantic. It was a period of time where people were able to grow grapes in the British Isles. Explorations were taking place that were going to Greenland and Iceland. Settlements were happening there. So it was a period of time that was known to be warmer, allowing these activities. Northern Hemisphere reconstructions of temperature showed to be warmer as well. In Western North America, we're finding it was a period that was characterized by periods of drought, periods of fairly persistent drought. And so these are 3 droughts in that medieval period, and I'll be talking about this medieval period because we end up having quite a bit of information about this.
So, Connie, some of these droughts lasted more than 100 years.
Mm-hmm.
I'm reading that correct?
Right. Now, the response time of the lake is a bit slower than like tree rings, and the dating, so you're going to get...
And even so.
Yeah, they were long droughts.
Is there research that shows why the medieval period, warming period happened?
That's a good question. It's certainly been researched, and there's a couple different things that people think it's due to. They think we're finding it was a period of time when the overall solar radiation was higher. That's recorded in the ice cores, and so it was a warmer period. There's also some evidence that the conditions in the Pacific Ocean were more like a La Nina, and that would make it more prone to have droughts in the western United States. There was also a period of time where there was more solar activity. There was, if you look at the sunspots, it was more solar activity than has occurred other times. These 2 conditions, though, they're not really unique, and so there's some question as to really what was going on here. As far as we know, there's no reason for these kind of events not to happen now. They're still trying to puzzle that out. Okay, so here's some more evidence from the lake, from the stumps. These are all places where there are stumps that are now in lakes and bogs, and these have all been dated. These are the dates that they were growing. These are the estimated periods of drought that correspond to those. And this is work that Scott Stein has done, maybe some of you have heard that. So again, sort of defining this period as one that had a couple of pretty good episodes of drought. Okay, let's talk about tree rings now. So again, these are shorter records because we're mostly relying on living trees, which again are limited in length. But they do have annual records, annual ring widths. But we can use this dead wood that can last in the landscape for hundreds of years in the right conditions. In the White Mountains of California, where it's very dry and it's very cold, this wood, it erodes on the outside, but it doesn't rot. It just sits there for thousands of years. But what we can do is with the living trees, we take the sample of an increment core, and we are able to, we know the outside ring is the current year of growth as we sample it, and then we can count back in time. What we can really use is the ring width patterns. When trees are sensitive to drought, there's a very distinctive pattern of narrow rings during drought years, and it's very very dependable. If the living trees overlap in time with the dead trees, you can match the pattern of the dead trees to the living trees, and if it overlaps, that pattern matches, we can then assign calendar year dates to the dead wood and use it to extend the record back in time. So that's how we get the longer records from the tree rings, even though the trees have limited length.
Do they do history match in the current years to validate?
Yes. Yeah, I'll show you. Is it next one? Yes. Here. Good question. These trees that are moisture limited, not all trees are moisture limited. If you go to high elevations, trees may be limited by the length of the growing season. But throughout much of the west, trees that are sort of at moderate to lower elevations are limited in growth by moisture. So here's an example. This is Russian River. That's not Wyoming, that's water year precipitation. The water year is October through September. Plotted with one ring width series, so measurements from one tree. So that's the ring widths are in black and the precipitation is in blue. And you can see it matches pretty well. I mean, the correlation is 78%. So it's the trees are really tracking the precipitation quite well. And we don't use just one tree, we use multiple trees. That's one of the advantages of the tree rings, besides having annual resolution, is, as you can imagine, it's a lot easier to go out there and collect tree cores than it is ocean cores or lake cores. So we've done that. This is a map of tree ring chronologies that are more than 200 years long, and the colors are different species. But each one of these triangles is not just one tree. When we go out to these sites, we collect about 20 or 30 trees. So these are all of the ring width measurements are averaged together to create a chronology for each of those sites. So these are more than 200 years long. These are more than 1,000 years long. So you can see we really lose a lot of the long records, but we do have quite a few in California and in some of the other parts of the West as well. Again, using that remnant material to help extend those records back in time. So with that kind of information, with a whole network of treeing data, you can actually do reconstructions of patterns instead of just one time series. And that's what's been done in this drought atlas, where this network of treeing data has been used to reconstruct the Palmer Drought Severity Index for every single of these grid points, going back from 500 to 2,000 years, depending on the area. And so with this kind of network of reconstructions, we can look at map patterns. So, for example, these are simple years of drought that we know were severe in California, and just from the instrumental data. 1990, 1977, 1924. This is the Palmer Drought Severity Index. This is really, really dry. This is sort of not wet or dry, and this would be very wet. And so you can see all of these years had statewide drought. 1924 being the most severe conditions, but really the smallest spatial. Yeah. These are three of the severe years in California, in the record for California going back in time, 1580, 1729, 1654, and you can see the difference in these patterns. Large areas of very severe drought conditions that really exceeded what we see in the 20th century. And then just here's some, this is just an example of a 5-year average. So 1987 to 1991, that fairly recent drought, we can see it extended from California up into the northern Rockies and the northern Great Plains, and then 1578 to 1582, much more severe, much more extensive. So just getting an idea of the spatial extent. And we're interested in the spatial patterns. So obviously, drought doesn't stop at California's border. And I think it's important. I know that Jeanine cares about that it stops at the border because California gets a lot of its water from the Colorado Basin. So it's important to understand, the spatial extent of these droughts. This one didn't go into Colorado, but most of the other ones did. So one of the other things that we're able to do is reconstruct stream flow from tree rings. So this is a reconstruction of the Sacramento River flow. I'm showing it back to 1,000 years, but actually it goes back to 869 up to 1977, and we're in the process of updating that. And then here's the instrumental record, the gauge record. So you can see this is that 1920s and 30s drought, which is pretty severe if you go back, to 1500. But if you go back before then, you can see droughts that are more persistent, more severe. So that's what's going on in Sacramento. We also have a reconstruction of the Colorado River, and that was derived from that's the chronologies. Here's what it looks like going back to 800 and up to 2005. There's the instrumental record. In this case, it's the 1950s drought that was a really big drought in the 20th century. But really, that drought pales in comparison to many droughts in this record. So the next question is, okay, so California gets water from the Colorado River and the Sacramento River. Are there times when we have droughts in both basins? Well, yes, but not that often. These are the two records, Sacramento in the brown, Colorado in the blue. And you can, if you just look at the 20th century, you can see, well, mostly the Sacramento is not doing the same thing as the Colorado, which is a good thing. But there are periods of time when the two are seeing low flows. Not too many, but there are periods of time. And the one that sort of sticks out is this one, the 1100s drought, which was in the Sacramento, was about 60 years of below average flow, save about 5 years. It's a long drought. It was pretty long in Colorado as well.
So you can take these and you work them into probabilistic models or statistical models of probability of events occurring, and then you can do strategic planning or emergency planning.
You could. You could. Yes.
Do we do that? Right?
Well, we don't. There's been a number of applications of treating data to water resource management. There's nothing that's quite been done like that. But there are some. There's some work in the Colorado River Basin looking at the Colorado River operations model and running this drought in particular through their model and seeing how the system responds at different lags. So it's not exactly what you're talking about, but there are applications that are starting to look at that kind of thing. They're actually, I've worked with a lot of water managers, but in truth, a lot of times they don't come back to me and tell me how they're using the data. So it could be that some of them are doing that. So anyway, this period looks familiar, the medieval period. It's a period where we have a higher incidence of concurrent drought, and it's probably not an accident. Again, we're not sure exactly what was going on with the warmer temperatures, with the La Nina conditions that might have been promoting drought, but something was going on in that period of time that led us to experience these more frequent and persistent droughts. And it isn't just the medieval period, this fairly significant drought in the 16th century. It was a short drought in this record compared to the 1100s, but it was a drought that we have evidence that occurred in northern Mexico, throughout the southwest, western United States, Colorado, drought a little bit later than the droughts we see here in the eastern U.S., so a significant drought as well. Okay, what about Southern California? We do have some treating reconstructions for Southern California. This is the network of treating chronologies. Actually, there's more now, but this is as a couple of years ago that existed for California. And many of these are from blue oaks. Do you know blue oaks? Familiar with those? They're mostly in this area here. And they're wonderful, wonderful recorders of moisture. The time series I showed you with the blue line, the black line, that was a blue oak. They're wonderfully sensitive to moisture, and they're extremely useful for reconstructing drought. I'm going to talk about a reconstruction for redlands. So this is a reconstruction of water year precipitation. So again, that's beginning of October through the end of September. It goes back to 1538 up to 2003. Here's the instrumental record, the rain gauge record, so you can look at that. This part of the record and compare it going back in time. And in this case, we don't really see something, as extreme as we're seeing in the flow records. But then it only goes back to 1538. We're not getting that medieval period. But we can look at it in different ways that helps us understand how it might be different. This is looking at drought duration and frequency. So what I did is I took that record of precipitation. I looked at all the 2 years below the average, the 2 years in a row below the average, and so on. So this is duration and of years in a row below average precipitation and the numbers of events. And we have lots of single years and fewer 2 years, and then we have a couple of 5-year, 4 or so 6-year events and one 7-year event. And this is just the 20th century part of that record. And it's interesting because there's more 3-year events in this record than 1-year events, but there's no longer events. And this is what you'd expect with a shorter record. The longer the record you have, the more likely you get those extreme events. So this is the same reconstruction, but I'm just showing you the 2 years in a row and 3 years in a row droughts and how they're distributed. So the orange are the 2-year, or the 3-year, the yellow are the 2-year, and then the height is how severe that period was. So we can see this clustering, which is, which is probably this bump here. We have a number of 3-year droughts in the last half of the 20th century. This is the most severe 2-year. But you can see that the distribution is pretty irregular. We've got this big hole here with none of these short droughts. Yeah.
Yeah, measuring the droughts, is that based on, do you do a correlation between the size of the rings and what you would expect as far as the growth?
What
to
we
determine the number of inches of precipitation, or is it sediments?
It's what we do is we have the tree ring chronologies, so that we've got a tree ring width measurement for every year, and we know that it's correlated with precipitation because they vary together. And then we use a statistical approach called regression. We just do a model. So we calibrate the tree ring data with the precipitation data. We get a statistical model, and then which is an equation. And then we just plug the tree ring data into that equation going back into time. So we're actually reconstructing inches of precipitation because that's what we calibrated against. So you don't do that with sediment records or any other proxies. The tree ring data are really the only ones that are actually calibrated with the actual climate record. So that's how we can do precipitation, because we calibrate it with the precipitation record, or stream flow, because we calibrate it with the stream flow record. So those are the 2- and 3-year events, and then if we look at the longer, these are 4- to 7-year events. We can see where that hole is actually a period of time when we've got a 7-year drought separated by 1 year that wasn't a drought year, and then it followed by a 5-year event. So the 1760s or so, pretty dry period in this area. Here's 2 back-to-back 4-year events separated by 1 year. That's that 1920s and 30s period that we saw in the 20th century as being pretty severe. So lots of variability. I guess again, getting back to looking at the 20th century and seeing if that's really representative of the longer period, being able to evaluate that, having these longer records allows us to do that.
So Connie, could you go back to that in a second? If I look at just from 1950 to 2000, there are 10 events, 9 or 10 events. And all the models are suggesting that the frequency and duration of droughts will increase with climate change. So I can't understand how this guy would make these statements yet. And if I were a water manager, I'd be very worried about droughts. And in one of your figures, it showed that we lose 10 to 20% of the average flow in the Sacramento to Colorado. That's the average flow. If you plotted it against low flow, then you really have
that's the thing.
problems that we face.
Right. So here's just the driest certain year period. So the driest 3-year period in the record is 1899 to 1901. Driest 5-year is 1668 to 1672. The driest 10-year period, the driest decade in the whole record is in the 20th century. The driest 20-year period, not surprisingly, was that period in the 1700s that had the 7-year drought, 1 year in between the 5-year drought. But then we get to this question, how relevant is the record of the past to the future? We've got climate change happening. This is a temperature record for California. This is annual temperature from 1895 to 2010, and we see this, it's not just one sort of a step jump, but definitely warming conditions going on. We see evidence of that warming in the snowpack. This is all these different data stations are showing winter precipitation and trends in that winter precipitation. Where it's red, more of the precipitation is falling as rain and less as snow. The little blue, which aren't not too many of them, are showing less rain and more snow. So this is in large part due to warming temperatures and their effect on precipitation. We also know that warmer temperatures during a drought is going to make the drought more stressful for plants. It's going to make water demand go up as people want to, water their lawns more, swim more. So these droughts of the future are going to have warming on top of them. So are these droughts of the past relevant to the future? The climate of the past is not going to be like the climate that we're going into because we have the effects of human activities. But the natural variability that we're seeing in these records, at least going back 2,000 years, There's no reason that those droughts that we see over the last 2,000 years couldn't occur now. There's no conditions that we know that we're operating in that are not possible to operate now. If you go back before that, like the earliest droughts I showed, things were a little bit different. Some of the major controls on climate, like the relationship between the sun and the earth, the orbital parameters were slightly different. So there were reasons why those 5,000 years ago conditions were a little bit more prone to dryness. But the last 2,000 years, really there's nothing going on. There's nothing going on that's different than could happen now. So those kind of droughts could occur. Warmer temperatures are observed, they're projected. That's, there's no ambiguity about that, we know. There's less certainty about precipitation. I don't know in California what the projections are, but I know in like the Colorado Basin, upper Colorado Basin, it's not clear what will happen with precipitation. But even with warming temperatures, as I said, that's going to exacerbate droughts. So we should anticipate droughts that are similar to the past several thousand years, but we should realize that you're going to have the added effect of warming on these. So that's a heads up. Yes?
How would, in climates where the ocean temperature is heated, you tend to experience a little bit more rainfall, from what I understand. How would that tie in with our river flow?
So areas that are more moist because they're near oceans, you're saying?
Yeah, as the ocean surface temperature is heating, that can cause more rain, can't it?
Well, yeah, there's in areas that are influenced by tropical moisture, for example, like along the equator. The thinking is that as there's more warming, there'll be more evaporation, more water evaporating into the air, more potential for precipitation in areas where it's wet anyway. So in tropical areas, that's the case. In places where the monsoon dominates, that could also be the case, although it's not clear what's going on with that. So in those areas, certainly we're seeing global warming mostly. I mean, there's a few places maybe that are more variable, but we're not seeing global warming or global drying because it's more complicated. You've got the global circulation is such that you have areas that tend to be wetter along the equator and areas that tend to be drier, like think of where the major deserts are. Those are areas where the climate is very stable. And then areas like where the westerly storm track goes that are a little bit wetter. So there's more variability, and that's what's a little bit trickier to say in some cases what's going to happen with the precipitation.
You
Yes?
said we should expect the added effects of warming. Are you talking about like more wildfires, the species shifting with the climate?
Yeah, I mean, there certainly are lots of effects. Fires are a really good one. In terms of droughts, that's one of the effects. Things like we've seen in many areas of the western United States with the droughts, the trees are weakening and they're subject to insect infestation, which kills them, and then you have more fires. There's a lot of sort of, no pun intended, downstream effects of these the warmer temperatures that have effects on drought, and then other types of effects too. Other questions? I think that's all I have.
Thank you, Connie. Anybody have anything else?
So it's probably fair to say that it's still going to be very difficult to plan in uncertain times, because as we add the complication of climate change onto this variable record, which we see is highly variable, certainly the global models, the climate models, are suggesting in the southwest during the United States we're going to get less precipitation. Almost all of them have converged. 1 out of 19 didn't project less precipitation in the southwest.
Yeah.
And but then, of course, last week we also heard, maybe for the first time for some of you, about these atmospheric rivers. Because you see, that brings a whole nother level of uncertainty into it, because we don't know how these complex changes in the climate are going to affect these atmospheric rivers, because there's enough rain in those atmospheric rivers to wipe out any drought, at least for a year.
Yeah.
So that, again, is still variability, but it almost still goes with this idea that we're going to see extremes more. We're going to have the same kind of variability, but the variability is going to be, so we're going to have maybe wetter wets and drier dries and stuff like that.
Yeah, I mean, as we go forward into sort of, we see this trajectory of warmer
Right.
temperatures anyway, but you see the variability of, say, moisture. You know, some of the periods of time they'll be favorable because it'll be wetter.
Right.
But if you get one of the drier periods, it's going to be exacerbated. It's difficult. I mean, I think that some of the water managers I've worked with in Colorado, it was sort of a, you know, they sort of, before about 2002, we had a really significant drought, they were pretty satisfied with looking at the instrumental record and saying, oh, well, this is, you know, the 1950s is a good guide for what we might expect. You know, this is our planning basis. And 2002 was a really, really dry year in Colorado, extremely dry, and it was drier than anything in their gauge record. And like, how often do we have a drought like this? And many of them started looking at the treating record after that and went, oh, there's all this variability from this longer record. And then now the final step is to go, okay, and then let's look at what climate change may add to that. So it's a huge spectrum of things to consider with planning. I mean, it's really a very challenging task.
But we pay people like Jeanine big money. Environmental policy and water management to deal with uncertainty. So when you look at California, as you say, all the models for down here, all of one, say we're going to be dry. In Northern California, change from snow to rain and maybe more actual precipitation, but we lose our biggest reservoir. So since one of the role of policymakers is to minimize regret for society, I ask you, Jeanine, since you're a public servant and we're paying your salary.
Not very much this
You're getting less all the time.
Given all of the uncertainty, when focusing on Southern California, if you wanted to protect us, knowing that we import, what, 65 or 70% of our water from the 50 from the north and 19 from the Colorado, how do we protect Southern California where 20 million people live? What would you do? You're running for governor, this is your 5-point plan.
Well, actually, that's when you close the state's borders, step number one. Because obviously, you know, the driver of many of California's water challenges is population growth. And that's why California faces proportionately more water challenges than, let's say, Wyoming, whereas they point out the antelope outnumber the people. But certainly things like more storage capacity in Southern California. Very little surface storage capacity here. There's been work in some of the groundwater basins, but still this area is rather storage deficient relative to the size of the population and the fact that you do live in a seismically active region. So the emergency storage, surface storage that you have in Diamond Valley Lake may sometime be tested sooner than you might wish.
And wouldn't you also want to diversify and expand the portfolio of sources?
Absolutely.
And you know, she's from the state of Arizona. They got 4 or 5 million people. You could close the whole state down. We could take their water.
You actually probably could, because we're junior.
We could annex Canada too. There's some Canadians that objected that. But you know, Jerry, getting to your question, I still think in Southern California that one of the biggest untapped resources is our wastewater.
Yes.
And you know, when we look at costs, and I just by way of historical, and back in the 70s, I ran the Army's water reuse program and actually funded the first international water reuse conference that was ever held in Washington, D.C., where we had 600 people talking about water reuse. But right now in Orange County at Fountain Valley, if you haven't been there, you should go and see the Orange County Water District, where we take wastewater and treat it to beyond any potable water that we have anywhere in the world. And yet in LA County, we're in LA County, in LA County we dump 450 million gallons of fresh water into the ocean. So clearly sustainability in Southern California, in my mind, has got to look at water reuse. We know it's safe, we know it's reliable, and maybe it's cheap, or maybe it's expensive, but it's only still a third of desal. But we have to be thinking about desalination because we can't eliminate that, but because it's so expensive, it should be the last alternative.
And I agree. I think it all depends where you are, and I think you have to, as you say, look at different sources and diversify the portfolio. There was an elderly woman at this event the other night, and she said, we all know about toilet to the tap, but I prefer to think of it as P to T, and I don't want to be drinking your pee. My tea, you know, that's us.
Well, but she doesn't realize that she's, you know, I did a calculation. In every glass of water that you drink here, there's about 1 or 2 molecules that Cleopatra pee
That's
out.
right, exactly.
So,
Absolutely. We have the same water we had on the planet
That's right.
4 billion years ago. We recycled it many, many times.
yeah.
And, but it's, the one curious thing is we treat it in Orange County to standards better than any potable water. But for public perception, we add it to the groundwater and it is degraded in quality and then we take it out and use it.
Yeah. Well, actually,
Now, does that make sense?
yeah. Actually, you know, I think I mentioned last week, we're actually moving forward with it. We're going to look at getting a grant from the National Science Foundation to hold a workshop on direct potable reuse, where we would take that water and actually pump it right back into your pipes. They've been doing that in Namibia. It's been since the late 70s, and the reason is because they don't have water. You know, when you've got a lot of water, it makes no sense to do reuse. But when you don't have water and you're going to die in 5 days, you'll gladly drink somebody's pee. But it's treated. I mean, you know, that anything, all the stuff that's in the wastewater is treated. When it goes through reverse osmosis, there's so little. I mean, we can't measure individual compounds above parts per billion or parts per trillion. In no pharmaceuticals and stuff like that.
Kind of, thank you. That was really good. And so, Jeanine, give us your running for governor. I'll vote for you.
I'll vote if you say water reuse. Put her into the political box.
Now, I suggest put it on the lapel on the right-hand side.
Yeah,
You're going to turn in that direction most of the time. Perfect.
Okay, so moving on from the water manager perspective here, this is what I'll be covering, just as a little outline. The last item, coming soon, warmer and drier, is really just sort of a teaser for what will be the fourth in this series of lectures. So, how many people here think they know what a drought is? This becomes actually a very difficult question when you're actually managing water. You can define drought in many ways. A meteorologist might say, well, it's when it doesn't rain or when the rainfall is less than average. A hydrologist might say, well, when the runoff in a particular place is less than average. And oh, by the way, like real estate, location is very important because drought is a phenomenon at a specific location or region. And if you are in the next watershed over, you may not think it's a drought while your neighbor in the adjacent one does. You may have seen the term regulatory drought used a lot in the papers lately, and that's generally used to refer to things like the Endangered Species Act that has provided protections for fish species, but at the expense of water supplies that were historically available for urban and agricultural purposes. There are many varieties of drought indices that can be used. Connie showed some slides from the U.S. Drought Monitor, which I'll get to in a minute. That's another way of attempting to depict drought. There are definitions that are based on particular sectors. If you're in the rangeland management sector, for example, you will have a different definition of drought than someone who is pumping groundwater and treating it for a local municipality, for example. So where you are depends, or what industry you're in affects how you define drought. Drought is really a function of impacts. And as I think I mentioned at the previous lecture, it's like the difference between a recession and a depression. The recession is when your neighbor loses his job, the depression is when you lose your job. Drought works the same way. If my water supply is okay, well, yeah, it's dry out there, but hey, it's no big deal. If my water supply is cut, all of a sudden it's a drought. So drought really is a function of impact, and impacts are generally localized in a specific area. So it makes managing things in a drought very difficult because you may have, for example, an elected official who wants to run off and proclaim an emergency related to drought. because it allows farmers to get low-income loans, for example. But on the other hand, if you look at the hydrologic criteria and you say, drought, what drought? And we run into these situations all the time in resource management. So the question of how exactly do you find drought and when is it really an emergency is not at all a simple one. I mentioned the U.S. Drought Monitor. Connie showed a different version of this page. This was actually from October 20th, showing, as Connie pointed out, that it's dry in Texas. The U.S. Drought Monitor is something that started out as a research project at the University of Nebraska, Lincoln, and with funding from many agencies and a lot of support from NOAA, has been supported through NOAA programs. It was kind of used as an indicator of drought conditions at the national level. It makes a pretty picture, but frankly, it does a lousy job for California. And every time we have a drought, people in my office have to explain to the news media why, despite what the Drought Monitor says, people are not dying in the streets in Los Angeles. Part of the reason is because the originators of this particular product, okay, Nebraska, how many people live in Nebraska? Not many. What's the biggest industry? Agriculture. Do they have a lot of irrigation? Not really, relatively speaking. So they tend to view the definition of drought in terms that are very related to non-irrigated agriculture. If you live in a state with 38 million people where we routinely move water all over the place, your water supplies may come from 400 miles distant. You're not relying on this year's rainfall to irrigate your crops. Your depiction or your experience of impacts in times that may be meteorologically or hydrologically dry may have nothing to do with that condition. And this has been a sore spot for us in the state of California for some time, that they haven't figured out how to better depict California's complex hydrologic system. It's very, very easy to find in a drought, especially here in Southern California. You can have two adjacent water districts in Southern California, urban districts. One of them will have declared it's a drought and is requiring a level of rationing from their customers. The next one, the one next door, has people in full supplies. That's a function of different supplies. Perhaps one of them is taking largely from groundwater sources. The other one is receiving its water from a water wholesaler who is reliant on imported surface water, which has had cutbacks. So deciding what to call a drought and how to designate it is not at all trivial from a resource management issue.
Don't you think it does a pretty good job though in Texas and Southern California that we don't have all this?
It certainly, in California, and we've had this discussion with NOAA a lot, and California is certainly at the top of their list of challenges because of the complexity of how we manage water. And two, this is also intended to depict dry conditions for all sectors, and it's very difficult to be all things to all people. You know, if from a rangeland manager, they would probably tend to be more in agreement with this because a lot of what they use to generate this is based on soil moisture and precipitation. But our state climatologist, for example, has had long conversations with the people who produce this product and update it weekly. We get a call from them saying, we want to declare California in a stage 1 or 2 drought. And let's say this call comes in July or August. And we want to do this because it hasn't rained in 4 weeks. Excuse me, it doesn't rain in California in the summertime? Yes, so this is a cultural thing when you're talking to people on the East Coast, but that illustrates the difficulty of trying to have one product be everything to everyone over a large geographic region, because that's not the way that works. Okay, so let's talk a little bit about managed and unmanaged systems as a follow-up to this.
So is there a California specific version of this?
No, and we have suggested that to them. We've also suggested that it would make our lives much easier if they simply whited out California from the map. Because it would reduce the number of truly confused calls we get from the news media, because at times the Drought Monitor will be saying people are dying in the streets, and in fact everyone has full supplies, and sometimes we go the opposite way too, because in past droughts, many of the water shortages that have been experienced by particular irrigators or communities deal with cutbacks for, say, endangered species purposes that aren't reflected necessarily in hydrology, but are a big cutback to a local supplier. So we have pointed out to them, actually we thought we would secede from the U.S., but they didn't care for that one either. So when we talk about managed and unmanaged ecosystems, remember last week when we talked about the Great Drought of 1862, which essentially wiped out the cattle industry in Southern California, wiped out that system of ranchos. That was an example of a time when there were no managed systems in California to speak of in terms of water resource capabilities. Now, fast forward to today, we have some systems that are unmanaged, and that would be rangeland grazing, for example. There's no irrigation involved there, to everything from the highly sophisticated water systems that we have in places like Orange County, for example. So we have the extremes. That picture there is 1935 in the vicinity of Huron in the San Joaquin Valley, on the west side of the San Joaquin Valley. At that time, the irrigation was primarily groundwater, if at all, very minimal. This is actually dry farmed barley being harvested. Now keep in mind that dry farmed aspect, because I'm going to come back to that later on for this particular area. So as we talked about last week, California has a very extensive system of plumbing that allows us to move water from one place to another, which is actually a very useful tool for responding to and dealing with droughts. And by the way, that's why Texas is always red whenever there's a drought, because big state but no plumbing to move water around. So anyway, just as terms of geography here, I'm not really showing here, but want to point out this is the State Water Project that moves water down to Southern California, diverts water up here from the Sacramento San Joaquin Delta, moves south. And then I'm going to be talking also about the federal Central Valley Project, which these yellow areas here, and I'm going to be talking about this area on the west side of the San Joaquin Valley a little bit later, and that's also where Huron is. So keep that location in mind. So this is just another way of showing that the reason that we have these major water projects in California is because people like to be where the water is not. This is showing rainfall and runoff by hydrologic region in California, much wetter in the north than in the south, but where's all the major irrigated agriculture and the people? They're largely south of Sacramento. And half of the state's population lives within the service area of the Metropolitan Water District. So we do have this mismanagement between where the resources are and where the demands for water are. So some of our more interesting droughts of statewide scope. This is sort of the master list here. And you can see in, say 110 years or so, we've basically had 8 multi-year droughts that were statewide in scope. And what kind of impacts did these have, or what's significant about them? Starting with what we call the Dust Bowl drought, 1929 to 34, which Connie mentioned. This is really significant to us because this was the first big drought, shall we say, when people started building water projects. The San Francisco system, the East Bay mud system going to the Sierras, and the hydrology of this particular drought cycle was the one that was used to design or to analyze the yield of almost all of California's large Sierra water projects. So this is Lake Oroville during the recent drought, in fact. If we talk about the yield of a reservoir, let's say that you build a reservoir that has a storage capacity of 100,000 acre feet. Does that mean that you're going to get 100,000 acre feet out of that reservoir every year supply? No, it doesn't. We use the term yield to mean how much water you can actually expect to get with some level of defined reliability from a reservoir. So for example, if you say that your defined level of reliability that you want to know about is the hydrology of the 1929 to 34 drought, you might find out that your 100,000 acre foot reservoir has a yield of maybe 20,000 acre feet. Of course, in wetter years, it will do better, but from a standpoint of looking at water supply, you want to know how it performs in a drought. Because as I said at the start of this evening, we manage for the extremes, we don't manage for the averages.
In that picture,
Mm-hmm.
is that for planning that the water level so low that it's not accessible? Is that an example of that?
No,
Or
it's
is it a water, or is it, you can see the shadow, is it,
this is basically just a low reservoir shot.
but it was it, okay, but it's not an example for planning that they didn't make it shallower, the dam?
The dam was basically designed to fit the site, to fit the physical topography of the site, and when you build a dam, you find a site that best meets your needs for range of supply and cost and et cetera, and you do these yield studies to find out how much water you will get from it.
So like in this situation, could you use pumps to pump it over that
No,
little bridge?
it would not be cost effective. This is kind of a situation you're stuck with. This is a reservoir with a storage capacity in excess of 3 million acre feet, and you can't pump out of that kind of situation. So 1976-77, this was only a 2-year drought, but this drought was really a wake-up call for water managers statewide. 1977 was the driest single year in the state's major hydrologic record, and you'll note that a distinct majority of California's counties declared local states of emergency at that time. That was because they were completely unprepared for drought. This was a very dry event. They hadn't had any significant droughts, in a couple of decades preceding this. Population growth had occurred, and they simply really weren't ready. And the classic poster child of not being ready that we like to point to is Marin County, which is the county on the north side of the Golden Gate Bridge. It's also a county that's always had a strong anti-growth sentiment. And we often find in droughts that there's a correlation between anti-growth sentiment and poor ability to respond to droughts. Amazing how that works. They don't invest in the infrastructure because of a fear it will encourage growth. And as a result, when a drought happens, you end up with things like an emergency pipeline across the San Rafael Bridge to bring them water. Now, our most recent really long drought was the 87 to 92 drought. And obviously we're doing better in drought planning because only about half the number of counties this time declared local states of emergency in the 6-year drought. And our 2 major water projects, the State Water Project and the Federal Central Valley Project, made full deliveries during the first 4 years of the drought. So no cutbacks until years 5 and 6, but those cutbacks were large in years 5 and 6. However, Southern California was particularly saved because the Colorado River supply was full, and that allowed urban users in Southern California to not be too adversely affected, with the exception of a certain coastal Southern California community that had a no-growth policy. That would be Santa Barbara. Santa Barbara was hugely impacted during this drought in terms of residential impacts. And although Santa Barbara had previously signed a contract to take water from the State Water Project, they had not yet built the pipeline to connect because of this no-growth view that was prevalent there. That did convince them to go ahead and get going and building that pipeline. The level of impacts that they had. Also rather concerning to us, San Francisco. Their system storage dropped to a quarter of capacity in the driest year of that drought in 1991. That's not a good place to be in, particularly since San Francisco, unlike many places in Southern California, does not have much diversity in their supply. They're a one watershed system with not a whole lot of local storage on the peninsula either. And this was actually the thing. San Francisco, pardon my pun, they have always been very insular in the world of California's water. And they have not played well with other water districts a lot necessarily. This was the thing that suddenly convinced them to become active in the water transfer market. And they actually started building some emergency interconnections to hook into some of our major regional plumbing, if you will, for the sole purpose of being able to take water transfers in the drought. I think this really pointed out to them that they had, because San Francisco has basically been at full build out for a long time, which is something you will notice if you ever try to find a parking spot in San Francisco. But because of that, because they felt they didn't have to worry about growth, so they weren't as worried about reliability as perhaps some areas in Southern California have been. Another area we saw lots of problems, small communities along the coastal area and in the Sierra Nevada foothills. And I'm going to get to those guys in a minute, but significant that this was a multi-year drought and these small communities were not able to cope. And they were doing things like water haulage. And you know, when you're at the point of hauling water in tanker trucks, I mean, let's face it, you failed. So just to point out, not all of our interesting droughts were statewide. There's a local drought in Southern California. Now, last week when we talked about how variable California's hydrology is, And we also talked about the fact that climate change is perhaps expected to exacerbate this variability, as Kelly Redmond mentioned. So keep in mind, in 2002 was the driest year of record, historical record, so 100 years plus or minus of record for some communities here in Southern California. Okay, very dry. What happened? We see water haulage again in some of the small mountain communities. Idlewild is a good example. Some over in the Big Bear area, some over in the Tehachapi Mountains. We see a lot of these small water system problems again, and of course, private wells going dry. We didn't see any impacts in the major water systems, Los Angeles, San Diego, anyone like that. And the 2003 wildfires, which is wildfires typically are related to drought, often related to drought, and this is something that we expect to see more of in terms of a context of climate change. But at the time of the 2003 wildfires, they were cited as the worst wildfires in U.S. history, period, in terms of dollar value. So, moving on now to our most recent statewide drought, the one we just completed. Guess what? Remember I said 2002, some communities experienced their driest year of record, like Los Angeles, San Diego. They did it again, just a few years later. So this begins to be a little worrisome when you get, extremes within a decade. Of course, we had more wildfires down here in 2007. And unlike the 1987 to 92 drought, when there were essentially no impacts to the customers of the big water projects in the first 4 years of a 6-year drought, we had immediate impacts in both the CBP and SWP in the first year of a drought. And notice that in the last year of this sequence, the Western San Joaquin Valley contractors, the Federal Central Valley Project, only got 10% of supplies. Well, what happened? Frankly, this is a reallocation of water to environmental purposes. Back in 1990, there was legislation passed called the Central Valley Project Improvement Act, which put the environment on equal footing with CBP project customers at that time. And then as part of the CalFed Bay Delta program, about 10 years or so later, more stringent water quality standards were put in place to protect the San Francisco Bay Delta. And then in 2008, we had new biological opinions, which are still being litigated, for listed fish species, salmon and smelt, that either reside in or move through the Bay Delta. And all of these things combined to significantly change how the water projects were operated to require protection for these species of concern. And this resulted in a very striking difference in the timing of impacts to the project customers, and also resulted in a lot of those protest signs that you see along I-5 as you drive south through the valley and that sort of thing. Also, I was going to say, also another area that actually had a similar situation in the Russian River system. The Russian River system, which is a river system north of California, north of San Francisco, goes out to sea at Jenner, very pretty little resort area, rustic resort area, is interesting because it suffers greatly on either floods or droughts. So it's kind of a poster child of dysfunction in a sense. But they too had some major conflicts in ESA requirements between requirements in a Federal Energy Regulatory Commission license for an upstream power plant that had diversions that supplied part of the river, and requirements farther downstream for endangered salmon that basically resulted in them being sort of tied up in a regulatory knot that they were in the middle of administrative proceedings to try and resolve, but they ended up with a 50% cutback to parts of their urban service area. So this is where you start seeing the term regulatory drought come about, and it was really mentioned a lot during these events.
What was it? The law in 1990 said that
Central Valley Project Improvement Act, or CVPIA, as we call it.
that was a federal or state?
Federal. Mm-hmm.
Before Judge Blocker and the Delta smelt, when you said the environment was put on equal footing, did that translate then into taking less water out of rivers? I don't just mean out of the Delta, other sources?
Well, to be really precise, when the Central Valley Project Improvement Act was passed, when a Bureau of Reclamation project is authorized by Congress, the authorizing legislation sets forth the project purposes and their priorities. So for example, in a typical Bureau of Reclamation project from, say, the early part of the 20th century, it would say irrigation is the first priority, maybe navigation in some of them, and then it would say power production is incidental. And often that would be all it would say. At the time the CDP was authorized, it basically set municipal and irrigation as the project purposes with a lesser priority for power generation, hydroelectric generation. Of course, this was authorized in the 1930s, so it didn't say anything about environmental protection. One of the things that CBPIA did was to say that environmental protection had equal footing with M&I and agriculture as a project purpose. And then it went on to dedicate a specified quantity of project yield, namely 800,000 acre-feet, for environmental, basically fishery purposes. And also another couple of 100,000 acre-feet was set aside in various ways for refuge water supply.
And have we stuck to that?
The federal government stuff, that's a federal, yes. But so you have, starting in 1990, you have a series of decisions which have essentially resulted in a reduction of supplies to what we call the South of Delta export area from the Central Valley Project, and that is the project contractors on the west side of the San Joaquin Valley, like in the area of Huron, where that barley harvest was going on. And also note that the State Water Project was also cut back, and that's why at the end of 2009, for example, you saw that Diamond Valley Lake, which is your largest surface water storage reservoir in Southern California, was basically at the top of its emergency storage pool. It's an 800,000 acre foot reservoir. They maintain 400,000 as emergency storage.
What year was the Calfed Delta project?
Well, the Calfed Bay Delta project went through a series of planning processes beginning in about, I want to say 98 or thereabouts. Signed a record of decision around 2000, more or less. But then as part of that whole process that was going on at the time, they also went through a proceeding with the State Water Resources Control Board to adopt new Bay Delta standards, call it early 2000s. Okay, so, and this, because of these impacts of the cutbacks of the Central Valley Project and the State Water Project, this was actually the first of our statewide droughts where we saw pretty large-scale impacts to irrigated agriculture in the managed project. Before, if we saw impacts to agriculture and drought, it was dominated by rangeland impacts, non-irrigated grazing, those kinds of things. But this time, you have the image of people plowing over their almond trees in the Central Valley and San Joaquin Valley, or pulling out orange trees, orange and avocado trees in San Diego and Riverside County, there because the interruptible water supply program that MWD had provided for its agricultural customers in Riverside and San Diego counties was being terminated as a result of drought impacts. And on the west side of the San Joaquin Valley, simply because of the cutbacks. And also related to Fresno County and the west side of the San Joaquin Valley, we actually had a governor's emergency proclamation that linked drought to provision of social services, i.e. unemployment, food banks, and that kind of thing. And I'm sure it was certainly exacerbated by the poor economy there. But to us, that was a very unusual thing to see, because that was the first time that this has happened.
I lived in Bakersfield the last 5 years, and I was living in Lost Hills at the time, and driving up and down the 5, they would plug whole orchards and they light them all on fire, and they're exempt from the burning law, so they can just burn as much as they want to clear land. And there were some cities like Mendota that had 40% unemployment,
Yeah.
and it was related to agricultural workers who had no jobs, but they used planting and produce water conservation.
Yeah, and there were some impact studies done back in the 1987 to 92 drought, and also after 1990 when the CBPIA was enacted, which created cutbacks for water in this area, and it definitely pointed out that these essentially small farm worker-oriented communities on the west side, Mendota, Huron, Avenal to some extent, San Joaquin, all those little communities really suffered because they have one industry and it's agriculture. So now shifting gears a little bit here, we'll talk about drought planning. Now, if you're an urban water agency and you serve more than 3,000 acre-feet or 3,000 customers annually, you're required to prepare something called an urban water management plan by statute. This was a statutory provision that came into existence as a result of drought. And every time we have another drought, more bells and whistles keep being added to it because the legislature can find something new to add to it. And it's actually one of the longest sections of the water code with respect to level of detail for a planning process. And urban water suppliers are required to prepare these plans and to submit them to us for review every 5 years. If you don't prepare and submit your plan, you don't have any access to a number of state financial assistance goodies. About 400 plus water systems in California are large enough to be required to fill out these plans. And essentially, they are a drought plan. They have a water shortage contingency section that says you must identify what you would do to cope with a 1-year cutback, a multi-year cutback, and a cutback of up to 50% in a single year. And there's also some thought that this was intended to respond to what would happen, how would you respond to an earthquake, knowing that California is a seismically active region. So what about people who aren't required to prepare these UWIMs, as we call them? Well, if you look at systems that are authorized by the state of California pursuant to the Federal Safe Drinking Water Act and the State Safe Drinking Water Act, you find that there are about 8,700 what we call public water systems. Public water system doesn't necessarily mean it's open to the public. It means a system which serves members of the public, could be either public or privately owned. It's a defined term in statute. Now, only about 5% of the state's total public water systems are big enough to have to meet this requirement to fill out UWIPs. And however, the other 95% of the state's public water systems generate the majority of the problem workload for the State Department of Public Health and for county public health agencies. This is kind of an example to use some other math here. We have 95 and 5. There's also a 90-10 split here, which is that about 10% of the state's water systems serve 90% of the state's population. But on the other hand, we have this huge number of what we call small systems, is the colloquial term that's used for them. And guess what? They're a huge problem in droughts. And you saw in the previous slides that I mentioned that we had problems with them, particular problems with them during drought periods. Many small systems have problems all year long, year in, year out, rather, regardless of water supply types. Typically, they're in isolated rural areas where they can't necessarily easily connect to a larger system to deal with their problems. They're systems that rely on unreliable groundwater sources, typically fractured rock groundwater or very small coastal basins that are too small to have more than a year's worth of water supply in them. Large urban water systems, we don't see a whole lot of problems with them in drought. You're not going to see the city of Los Angeles running out of water. And except for those areas that have been a little touchy about growth inducing or allowing growth or enabling growth, the Marin Counties of the world, the Santa Barbaras in the past, who were rather lax in their planning because they didn't think they needed to. Big urban areas, they have money. They can generate the money to do capital projects, to do water transfers, to do things to help them mitigate drought impacts. Not true in small water systems. And this is where we actually see public health and safety impacts. We see things like boil water notices, we see people hauling water. This is not good. And by the way, the other category where you see a lot of impacts in the public water system sector, urban sector, private single-family residences on wells, which are only very lightly regulated. And where are these fractured rock groundwater systems that I mentioned? Everything in blue on this map is what we have designated as a groundwater basin, meaning that typically this is sort of like an alluvial valley that has a lot of nice soil in it that acts like a sponge, holds the moisture, you can pump water from it. The white areas tend to be largely mountain ranges. And see essentially everywhere, not sure not very well, basically all these white areas along the coast and the interior foothills, The foothills in Southern California over the Inland Empire area, the foothills in the Central Valley. Those are problem areas. They're hard rock groundwater basins. They're not necessarily very good sources. It's not like you have this nice kind of standing material that acts like a sponge. You can put a well in and expect water to flow to it. If you're really lucky, you may have a fracture pattern in your groundwater where you've drilled your well and the fractures intersect, and maybe it holds some water. On the other hand, maybe it doesn't, and this is why you hear people who live up in a foothill area saying, well, I have to drill a new well and I hope we'll hit water this time. That's because the water is not that easily found in these kind of conditions. And typically what happens when you have a failure of your system is you do end up with this truck haulage of water. In extreme cases, if it's a privately owned system, which is not uncommon when you get down into these small water systems, it's not all that unusual to see the owner-operator of the system walk away and dump the problem on the county, who is not at all happy to become the provider of last resort. Some counties are very proactive about working with small systems that are under their jurisdiction of their health department and trying to help them improve their conditions. Los Angeles County, for example, does a really good job of working with small systems in their area. Other rural counties that don't have a lot of resources tend to not do a very good job because they don't have the resources to do it. So now the little teaser for what about droughts in a future with global warming. And speaking of global warming, this is NOAA's current list of the top 10 global warmest years. You notice that there's only one of them that was before 2000. That's kind of an interesting little point. And one of the things, even if you had the exact same water supply, one of the things about warmer is that your water use increases. And when you have a drought, does your water use go up? Yes, it does. Because under normal conditions, some of your water demands are being met by rainfall for irrigating your lawn or for irrigating crops. If it doesn't rain, then you have to take water from your groundwater system or your reservoir to do these things. So water use actually goes up during droughts. And water use goes up when it's warmer with respect to plants. So this is not a good combination here. And last slide here. And this is the National Geographic Submersible looking at some of those tree stumps on Lake Tahoe. Our existing infrastructure was not designed for some of these major droughts that Connie talked about. And certainly when trees, some of which are as deep as 30 feet under Lake Tahoe now, were growing on dry land, that is not the kind of drought that our system of infrastructure has any real hope of dealing with. And even in times that were much more recent than that, Connie referred to the medieval climate anomaly, or as some folks like to call it, the medieval megadrought. That's certainly much worse than we've experienced in our historical record. And as the climate modelers who run these global climate models are telling us, basically the dry gets drier. So if you're in an area like Southern California, which is already relatively arid, you can expect a drier future. Now might be a good time to think about replacing that lawn with some more drought-tolerant plantings. Anyway, so that's my last slide. Happy to answer any questions.
Who has the first one? Yes, go ahead.
Well, I remember last time you said sometimes this kind of legislation to change these things can take a long time or it needs a wake-up call. Would you compare that to maybe like what happened in Long Beach in the 1933 earthquake, how they weren't ready for such a big earthquake, and it took that kind of an earthquake for building codes to be enforced and legislation to change? Do you think we're going to need to experience one of these historic droughts before things actually change?
Well, experiencing drought always helps legislation along, and the UWIPs that I was talking about there is a good example. That legislation was first enacted in response to actually the 76-77 drought, and every time we've had a drought or some dry conditions since, they tend to keep adding more to it, and that's one reason that author of that statute is now so long, because they keep coming up with new things to add. But yes, a drought or a flood on the wet side is definitely something which makes resources available, whether it's financial resources in terms of state financial assistance programs for local agencies, or it's legislation that tries to deal with some aspect of it. We tend to be reactive rather than proactive.
I was just trying to check the score of the World Series, but I got it.
Other question? Yeah.
Has the state started looking at adaptation locations for coastal residents or people in very dry areas of where should development be happening that's ideal for future trends?
Well, you know, it is, local land use control is a dearly cherished local prerogative. And back about, I want to say 15 years ago now, the legislature took the first baby steps toward requiring local agencies that have land use authority, and that would be cities and counties, you know, that can do zoning, to, for the land use approving agency to actually consult with the water provider for development of subdivisions of greater than 500 units. And that was an intense, there were actually a pair of companion bills that were intensely contested in the legislature. You had the Building Industry Association on one side, you had the Farm Bureau and the environmental community on the other side. It was a brutal legislative session to get that through. And at the time, the authors of those bills basically said, you know, we know there's some imperfections in this. We know it's a first step, if you will. But this was such a miserable legislative session to get this through that we're going to set this aside for about 10 years and see how it works, and then we'll come back and revisit it. There have been some suggestions that it might be time to come back and revisit it occasionally, but so far no one has had the institutional fortitude to do so, and we haven't had a major drought. But this is a long-standing issue at the local government level, because the water district is required, whoever the water purveyor is required to serve whoever lives within their boundaries, but they have no control and no say over that. That's entirely the city or county that has the land use powers. In terms of adaptation, some local jurisdictions have been really motivated to start thinking about the sea level rise aspects more than anything else. So sort of on the flood side, if you will, or the wet side. City of Santa Cruz, for example, was really one of the early leaders in this area, explicitly recognizing in their local zoning and growth planning that they would not allow future development in areas that were expected to be inundated. But with respect to drought, there always seems to be the feeling that, you know, we can keep on approving development and we'll just sort of figure out how to make that happen. A couple of the big political arguments that you see at the local level, one of them is, well, we will just meet a lot of that new growth through water conservation. Which is actually putting the burden on the back of the existing ratepayers to subsidize future growth, which many existing ratepayers find problematic, especially when the water bills start going up. And another one is the issue that water transfers will solve everything. And when the urban water management plans were first being required, there were fewer bells and whistles required of them initially, and there were fewer things that local agencies had to have a UWIMP for in order to be eligible for state funding, for example. Well, the requirements on UWIMPs keep getting stricter. Initially, the law just said, well, they will submit them to the Department of Water Resources. But now they have to not only be submitted, but if you want financing, we have to approve them. But something that you commonly saw in almost all of the early generation of UWIMPs was they would go through this detailed water budget of how they would meet their expected shortfall in a dry year. And they would say, well, new well, 20,000 acre feet, new connection to another system, 15,000 acre feet, water transfers to be determined, 70,000 acre feet, meaning that they just identified the 2 or 3 projects that they knew they were going to do anyway, and they just said, oh, we'll take care of the rest of it with water transfers.
Jeanine, you've got to update one of your slides. It needs to say that in areas of extreme drought, the probability that your baseball team will win the World Series goes up.
Exactly.
So that means Texas won. Not predictions, but scenarios are plausible pathways to the future. Tell me if this is a plausible pathway to the future for Southern California. By 2050, population is 25% greater. The increase, there will be an increase in the frequency and duration of droughts. Water use increases during droughts without even adding the population. Water increases as the temperatures warm, climate warms, and small communities will suffer first and earliest. When it hits the big cities and the agricultural economy, nature will lose. Now that's Jerry Schulman's interpretation. Yeah, I think, but do you think that's probably fair?
Well, I definitely, if we look at where drought impacts health and safety level, what I would call health and safety level impacts have been experienced in Southern California. It's your small communities, right, either on the coast or the Inland Empire foothill sort of communities, the small ones. Julian, for example, San Diego County, lovely place. Boy, do they have water supply problems. And every time there's a drought, because they're a fractured rock groundwater system.
We have time for other questions and comments. This is a good opportunity for you to ask some questions. Yes, go ahead.
What's the status of Long Beach Water District and water sources situation?
The status.
As far as you have a good WIC program, a plan.
City of Long Beach, rather. City of Long Beach has been very active in planning and looking at new sources in pursuing conservation. They were an early investigator into things like some of the desal and water reuse programs. They do have the disadvantage of being at the extreme downstream end of the system, which limits some of the options they have available for them. But at one point, the City of Long Beach was actually looking at using the harbor as part of a water storage project, if I recall correctly. It was an interesting concept.
And in the final evening of this course, Kevin Wadier, who is the manager of the Long Beach Water Department, will be one of the people who will speak. It has been a pioneer, very forward-thinking, and they challenge some of the statements of the Metropolitan Water District, which says everything's going to be fine, don't worry. And Kevin says, that's crazy, there's not enough storage capacity. So I think you will enjoy Kevin's comments. Others?
Maybe if I just
Yes, go ahead.
quick pause to say, next week's session will be on flooding, and there are areas in Southern California that are at higher flood risk or have more issues than others. Long Beach does have some interesting challenges because of its low elevation related to the ocean being next door, and with climate change exacerbating both the frequency of extreme storm events as well as the sea level rise component. I think Long Beach is one of the cities that's going to have some work to do in their stormwater system.
Other questions, comments? Anybody? No? You ready for the test?